So our final speaker is Tom Rovis, and Tom originally did his PhD at the University of Toronto, and then with Mark Lautens, and then postdoc with David Evans, and then began his independent career in 2000 at Colorado State University, and as another person who's had an amazingly fast rise in his career, because by the time he'd been there for 8 years, in 2008, he was already had the John K. Stilley Chair from the university. In 2016, he moved to the University of Columbia, and he's been recognized for many awards, of course, the ACS Scope Scholar Award, and then more recently, the Alexander von Humboldt Award. And so Tom has actually had big impacts on many areas of chemistry. He's very creative, as you'll see from his talk. He was one of the leaders in driving the early generation of the nucleophilic carbines and all the new chemistry that came out of that system. But instead of staying in that area, he also had several other projects related to transition metal catalysis. And these have now evolved very nicely into really exciting CH functionalization applications. The only complaint I can give about Tom is that he's used my title for his talk. So the title of his talk is Selective CH Bond Functionalization. So Tom, welcome. We look forward to your talk.
I knew you were going to complain about something about me. Thank you, Hugh, for the invitation. Where's this share the screen button, Rio? I don't see it.
Should be on the bottom of your Zoom.
Oh, right there, right in the middle, right in front of me. So I've got a remote here, so I'm going to try it this way. Bear with me just for a second. Oh, that's not what you want to see. You see this? How are we doing? More importantly, can you see the laser pointer?
Yes.
All right, great. So thank you again for the opportunity. Indeed, as Hugh said, I've done this once before. It was still at Colorado State, so it was quite a few years ago. You know, I remember thinking at the time that this was an interesting new development, this virtual symposia. And I thought, it's just not the same as an in-person meeting. But this was a visionary thing that you guys did, and I have to give you a lot of credit for it, because clearly today, for unfortunate circumstances, we're all very much enjoying this, and this may be one of the major meeting styles going forward. So nice work for the center. I thought I would tell you a couple of stories today, and it's all based around CH activation, of course, since it's the relevance of it. I tend to start with an introduction like this, and a molecule that's as simple as this one that I've got shown on the slide, a long N-alkyl chain, alpha to some sort of functional group. How do you functionalize this? If you wanted to do selective, and again, it's always selective functionalization, how do you do it? So we've known for a while the rhodium and iridium catalyzed borylation chemistry is exquisitely selective for the terminus. So the methyl is accessible. Hugh's group recently has developed some really interesting dirhodium catalysis with these diazos that goes after the sterically most accessible but somewhat electronically activated methylene, the one adjacent to the methyl. And of course, there's much older chemistry that activates the methylene adjacent to the functional group. That tends to be strong base type chemistry, almost regardless of what the functional group actually is. That is the most kinetically acidic CH bond. Every other position, for all intents and purposes, is inaccessible by what we know today, unless, of course, the functional group can be changed into some sort of often elaborate protected group. So here's an interesting thing. My talk is actually being interrupted by my dog, who's trying to get into the room. All right, I'll show you a picture of the dog later. So this functional group is, I would argue, or at least this molecule, is of intense academic interest perhaps, but not really practical interest. Very rarely do we actually have a molecule that's as simple as this one with just many unactivated unique methylenes. Much more often we're looking at functional groups that all of us as chemists face: ketones, alkenes. Selectivity among ketones between two different positions, assuming it's an unsymmetrical ketone, is a long-standing problem with some nice solutions in the literature. I would argue at least the thermodynamic solution is still not great. I'll show you that a little bit later. Alkenes, on the other hand, there are some insights, but this the terminal alkene activation is only one methylene, but the functionalization of that intermediate is still not general. And then an internal alkene is, I think, a much bigger challenge. Of course, you can apply the same analysis to ethers, and asymmetrical ether has two different positions, as we saw in Abby's talk, for example. And of course, amines, both tertiary amines that are unsymmetrical, as well as primary amines, which have sort of the same challenges as this molecule at the top. All that being said, these are still fairly simple molecules that I'm showing you. We as chemists, including medicinal chemists, natural product synthesis people, face much more complex targets. So the method that we want to develop doesn't just have to activate simple molecules like I've shown you in the last slide. It should ideally also be applicable to much more complex settings like these. Pharma makes these intermediates. Ideally, they don't want multiple natural product syntheses of a single target. They want to diversify something late. And again, we've seen examples of that as well in the talks today. Okay, I want to draw your attention to one molecule up in the corner here. There's actually several of them that have this this bi-aryl relationship here between the two aromatic cores. There's actually a couple more in these. And there was an interesting, we talk about as chemists that methods enable drug development. And it's sort of true, but the problem is that methods also determine drug development. So CNN News wrote an article a couple of years ago, this is from 2018, noting that pharma had all of a sudden identified many drug targets, including the one I've shown here on the slide, that had a bi-aryl, an heteroisomer. And these heteroisomers were interesting pharmacologically. And while that's true, a couple of years earlier, there was several reports, and I just highlight one from JMed Chem, noting that of all the reactions that have developed, that have entered pharma, number one, if you can see it down here in the graph, is an amide coupling, and number two is the Suzuki. So we have a method, and we generate bi-aryls. And big surprise that that method then translates into many pharma targets, or at least potential drug candidates. And in fact, the real problem, if you can look at this slide, is that the three-dimensional space of molecules is in essence dictated by what we can make. So what do we want? We want to make anything. We want to make something general. So where do we start with that? I would argue as synthetic chemists, we look at places like Aldrich and what's available. And certainly our bias is that we want a polarized bond, something like a CX, a halide. Of course, carboxylic acids are also available, amines, and more narrowly primary aliphatic amines. But if you look at Aldrich, alkyl halides are actually nowhere near as commonly available as carboxylic acids, and amines trump carboxylic acids. And if you think Aldrich is biased, well, maybe, but a large source like enamine, the trend is the same. Halides, 8,000 unique halides, 25,000 carboxylic acids, more than 40,000 amines. And Pfizer's internal database reportedly has 30,000 unique halides and 47,000 amines. So if you want to start with something generic as a starting material on the simple end, you want things with nitrogen in them, primary or secondary, tertiary. And keeping in mind that pharma works on many things that possess nitrogen. So the methods that you develop to functionalize molecules like these two, ideally should also be susceptible or applicable to molecules like this, where you want to do, again, one total synthesis of this target, and then a series of steps individually and selectively append the various functionalities around that core so you can interrogate three-dimensional chemical space further. Okay, so I'll actually tell you two stories today. One is functionalization of alkenes. And again, primary alkenes, but really, excuse me, alpha olefins, but really more relevantly, internal alkenes, and then selective functionalization. And the second story that involves, quite frankly, very different technology is to functionalize primary and really tertiary amines selectively on symmetrical tertiary amines at various positions. So the first story involves Rhodium-3 catalysis. We've been active in this field for a decade now. In fact, our first paper is down here. Todd Heister, when he was still a graduate student with me in 2010, right around 10 years ago this month actually is when we submitted it. And we've since reviewed the entire contributions that have come out of our own labs a couple of years ago. And I'll try to summarize for you sort of the state of the art in the field as it's still relevant. Huge majority of people in this area work on reactions that are delivered by some sort of directing group. That tends to be on an aromatic core, but sometimes it's vinyl. It's almost always Sp3 Ch hybridized here. The catalyst is almost invariably pentamethyl cyclopentadiene rhodium-3. It's a piano stool complex. There's always a base, and the base tends to be something that looks like a carboxylate or a carbonate or something to do the considered mylation deprotonation. The directing group varies. It's certainly started with things like pyridine. We've migrated much more to things that are more commonly found in organic functionality, including carboxylic acids, amides, etc. There's a reacting partner. This is a weak bond of some kind. Every weak bond you can imagine has been applied. I won't spend a lot of time talking about this. The product then is in the net addition of that CH bond across the weak functionality with, of course, some caveats. And then one of the best things about this technology and these reactions is the immense solvent tolerance. Some reactions work best in toluene, others in water, and everything in between. The temperature tolerance, room temperature 110, we've actually got reactions that work at -10. And then not all of these, but many reactions are oxidative in nature. And the oxidants that can be used is also quite diverse, including sometimes oxidants inside the molecule itself, an NO bond here, an NO bond here, etc. Okay. So what was missing from a lot of this, as I alluded to earlier, was activation of Sp3 Ch bonds. And on the basis of some chemistry that I don't have time to tell you about, we looked at a substrate like this, and this was Jack Conway when he was a postdoc with me. And what we expected is to activate this position and insert a pi system of some kind with rhodium-3, and we hope to get a structure like this. If it didn't do this sort of interesting reaction, we thought maybe it'll activate the CH bond, the vinyl, at one of these positions. And I've just drawn one potential product, and that is cyclization here to make these large eight-membered rings. Neither happened. Instead, what Jack found is that the rhodium actually activates the alkene for diamination chemistry. So we add one nitrogen on one end of the alkene, and clearly the starting material, another molecule starting material, has participated as a nucleophile to diaminate. It's not very effective, but Jack managed to optimize it. And now he gets a diamination catalyzed by iridium instead of rhodium. So rhodium-3 migrates over to rhodium-3 analogous chemistry, and you get this diamination chemistry. We can control it. We can get either the delta lactam or the gamma lactam on the basis of some manipulation of reaction conditions. So that was in 2018. A talented postdoc arrived towards the end of Jack's time with me, and he looked at carboxylic acids. This is Hungwei. And we found that carboxylate as nucleophiles also did the same chemistry. We modified the iridium-3 catalyst to get this alkoxy amination, either delta or gamma lactam selective on the basis of the electronics and sterics of the catalyst, completely complementary. And one other thing I'll tell you about in all this is an observation that Jack had actually made, and that was with variously substituted hydroxamate esters with R equals H here, the diamination product is generated in good overall yield. If you put a methyl at that position, the yield drops significantly, 38%, and what you get is a significant amount of the loss and rearrangement byproduct, i.e. the hydroxamate ester eliminates pivalic acid to make a nitrene or a metal nitrene intermediate. That does the courteous type loss and type rearrangement to make an isocyanate, including the amine traps. So all of that suggested to us that the active intermediate in all of this chemistry, oh, one more thing, if you electron deficient alkene actually can shut that down. And that suggests that there's either a rate acceleration with this electron deficient alkene or the iridium is actually on the nitrogen during the migration event. And that suggested that the key intermediate is something that looks like this, a iridium nitrenoid of some kind that engages the alkene, either delta lactam formation or gamma lactam formation. I'll note at this point some very nice work that has emerged out of Chang's group in South Korea. Paper published in Science would also manage to harness these iridium nitrenoids as intermediates. And probably the most surprising thing about it, I really want to drive this point home, is that you don't need X group here. You can tolerate carbon, and it still, for I think subtle reasons, still avoids this loss and rearrangement to this courteous type rearrangement. Okay, so that was in 2018 or so. So one direction that we wanted to take this is if it actually is generating these iridium nitrenoids, can we do then intermolecular activation of alkenes instead of intramolecular activation? Now, obviously, greatly, I would argue, expand the synthetic repertoire of this reaction. And thinking about that, the first step of this prototypical terminal alkene activation is actually known for a variety of metals. You can generate these pi alls, and then nitrogen nucleophiles have been incorporated. They inevitably end up at the terminus of the alkene to generate the internal, the thermodynamically more stable alkene. We felt that if this was an internal inner sphere nitrene delivery, that it ends up on iridium, and because of the oxidation of these dioxazolone, it would end up on iridium. We hoped that it would end up at the internal position rather than terminal position and give a complementary product from terminal alkenes. Long story short, it did. Again, we moved from Rhodium 3, top reaction, about 3-to-1 selectivity, regioselectivity, and modest yield, to Iridium 3, CP star Iridium 20-to-1, exquisite selectivity for the internal, the chiral product, the branch product, and 75% isolated yield. I won't belabor the scope extensively. We've published this about a year ago now. We tolerate reactive functionality. We tolerate sterics, including a benzylic position is reasonably tolerated. The regioselectivity is exquisite in nearly every case and good chemical yields in most cases. Because, again, these dioxazolones allow you to introduce various R groups here, and because the iridium nitrenoid does not undergo this loss and rearrangement, that means we can introduce various amides by this chemistry. We illustrated several of them, a long alkyl chain in the bottom, tert-butyl, of course, an aryl, a vinyl we have an example of, and then a functionalized alkyl as well. Okay, so that was a terminal the mechanism, just to go over it very briefly. So we believe that we need an open coordination site in iridium. We coordinate the alkene to have and then this sets it up for the considered methylation deprotonation, the activation of the allylic position. That eliminates acetic acid and gives us this piallyl. We actually have crystal structures of various of these intermediates, and I'll draw your attention to the piallyl. This is actually stabilized by sulfonamide as an exogenous ligand, which is presumably when the acetate dissociates and then the dioxazolone comes to coordinate at iridium, or here. That generates, we believe, the iridium nitrene, and that does the intersphere reductive elimination to give you this intermediate before catalyst falls off and turns and releases the product. I'll also point out that right around the same time that we published our work, the Glorious group at Munster and Simon Blakey at Emory published nearly identical chemistry, same target, same types of products, some very nice and complementary work. So that was a terminal alkene. And like I said, in terminal alkene, the challenge of CH activation, the selective CH activation is gone. There's only one CH. Then it becomes a challenge of where you aminate. And iridium lets us solve that problem. We then turn our attention to internal alkenes, and in particular, unsymmetrical internal alkenes. And a molecule like this internal trans alkene that has two distinct allylic positions can clearly metallate at either one of these, the top pathway or the bottom pathway. And then it can aminate at either one of these two positions to give you ultimately 4 different products. And we thought this would be a great challenge. There's no good solutions towards this. We were realistic, I would argue, that this could be potentially an insurmountable challenge. And we thought we'd simplify the system just a little bit and also take a look at 1,1 substituted alkenes to have some of the same problems. They still generate 2 potential piallyls because of 2 unequal allylic positions. We thought the situation would be simplified a little bit because the piallyl, at least with iridium, we felt should give us exclusively this amino, selectively this allylic amination product rather than the more thermodynamically stable alkene, but less desirable linear type product. So that's where we started. We optimized reaction conditions. I won't say about that in a lot of detail, but we find that these unsymmetrical alkenes undergo regioselective amination with this system in exquisite regioselectivity. So a trifluoromethyl group that's 3 carbons away, I guess 2 carbons from the alkene, allows completely selective allylic functionalization internal, distal to the electron deficient group, 80% yield, better than 20-to-1. In fact, more or less any kind of electron deficient group, including an arene as an electron withdrawing substituent. If you move the trifluoromethyl 1 more bond away, the regioselectivity drops from 20-to-1 to 7-to-1, but it's still synthetically useful, even when it's 4 bonds away from the reacting site. This amide derivative is very reactive in our system. This is actually a challenge for most electrophilic amination protocols, and in our case, it's not a problem. 2 different oxygens, a tosylate and a siloxy group that are equidistant. The less electron deficient one prefers alpha, so 79% yield, only 3-to-1 selectivity, but it's basically between 2 different oxygens. And then last thing I'll tell you is that if there's a methyl on one side, whatever's on the other side wins. It never goes after the methyl. So methylene selective over the methyl to these alkenes, which in theory can, again, you can think about putting into more complex systems. Again, as I mentioned earlier, if you use a substitute dioxazolone, you can bring in various different amide groups on that nitrogen. So why does this work? What's the source of the selectivity? And Hungwe put a lot of effort into this, and most of the things, certainly all the things we thought at first, didn't answer the question until he got around to looking at J1CH coupling. So these are actually known to be an indicator of the percent S character in the bond and a reflection of the bond strength. So you can measure these J1CH at the two allylic positions, and then you can measure the difference in the coupling. And the larger the difference, the greater the selectivity. So 2.6 to 1 delta 2.6 hertz, 35 to 1 selectivity. As it drops to 0.2, next to no difference, 2 to 1. Note in this arrow series, these are exquisitely sensitive actually. So an electron deficient arene has a 1.6 hertz difference in coupling, 14 to 1 selectivity. As you get progressively more electron rich, it's only 1.2 now, 9 to 1 selectivity. And clearly it graphs. In fact, it literally graphs the selectivity with a decent R² value, with one significant outlier of the ones we looked at, and that's this one. And that's a phthalimide-containing system, which quite frankly we think undergoes competitive coordination between the amides of the carbonyls, of the phthalimide and the iridium catalyst. Internal alkenes have a different problem. So we also looked at a molecule as simple as 3-hexene with obviously no difference in these two. This is a symmetrical system. It'll make a single pi-al intermediate, where the challenge now is going to be, where do you aminate? So under these conditions, the amination actually happens indiscriminately. And I would argue that if we had done this experiment first, we would never have done any other experiments because it just wasn't promising. But we knew about the one with the substituted alkene and these distal electronic effects on the CH activation and the amination. And we felt if we put an electron deficient group on one side, potentially this will be selective. And we went all the way to the tosyloxy on one end, and this end goes completely selective allylic CH bond functionalization for the blue path, 20 to 1, and then the amination is also selective. In this case, only about 6 to 1 or so under these conditions, but certainly synthetically useful. So you can take these elaborate systems that are potentially present in much more complex molecules and still do selective CH activation. How long we optimize this as well? I won't go through all of these, except the ones we settled on, which is this trimethylsilyl methyl CP derivative as a mixture of electron deficient and sterically more accessible. It gives us high chemical yield and Regis selectivity. In all these cases, the red dot signifies the minor isomer. The amine ends up here, the alkene here. But as you can see, it's reasonably tolerant to a variety of functionality. If you don't have two allylic positions, it'll still activate. These are very electron deficient alkenes that still activate the gamma position of the electron deficient enoic acid or the enoate or the styrene, and good Regis selectivity and good chemical yield. Okay. I'll switch gears a little bit and talk about the amine fungus. Abby's already given, I think, a nice introduction to photoredox. Maybe I'll just give you my spin on photoredox itself. This is an area that we've been in for a long time as well. The heart of photoredox is the catalyst or the dye or the acceptor. And I've drawn just here, just to illustrate this point, the prototypical one, Rubipi, which is, I think, probably one of the oldest ones, certainly the oldest transition metal one. The ground state of a Rubipi has electrons in the d orbitals of the metal. Once exposed to visible light, in this case it's blue, one of these electrons gets elevated up to the LUMO. The LUMO is ligand centered. That generates a singlet first that then goes to a triplet. It generates an oxidant because it has a hole here, and it generates a reductant because it has an extra electron in the ligand sphere. So this molecule, this excited state intermediate, is both an oxidant and a reductant at the same time. You can clearly quench it either way. I illustrate here an oxidative quench that generates a stronger oxidant, which is known to be strong enough to oxidize tertiary amines to radical cations. And the chemistry that I'll tell you about goes through this intermediate. One of the subtlety of photoredox, and actually Abby alluded to this as well, there are really more than three, but three major scenarios for photoredox. The photocatalyst is the oxidant, where the donor donates its electrons. Clearly the orbitals have to be aligned. Photocatalyst gets reduced, the donor gets accepted. That's with tertiary amines, for example. The photocatalyst is the reductant, where the acceptor accepts the electrons. The dinitrobenzene, I didn't really talk about that, is that situation where the photocatalyst is now cation, the generated intermediate, and the acceptor, of course, is radical anion. Or there's something called energy transfer, if there's a match of both the movement, in essence, of the higher energy electron and the acceptance of the lower energy electron. The net transformation takes a triplet of the photocatalyst and generates a triplet of the acceptor molecule, including a transition metal complex, for example. Okay. So we've been involved in this area of amine functionalization for probably about 5 or 6 years now. And we've started looking at molecules, again, as simple as this one that I alluded to earlier. Can we activate various positions? We can activate the 1,5 on the basis of 1,5 hydrogen atom transfer chemistry. We've disclosed that. We can go 1,2 on the basis of several complementary chemistry, including some involving cobalt. 1,4 is something that's going on in the group right now, and it's just much too early to talk about. And 1,3 is also something that's going on in the group right now. Primary amines, of course, are not the only subclass of amines. Tertiary amines are also a huge subclass. And in fact, tertiary amines have an additional problem unless the amine is symmetrical, and that is two different positions. So let's just say N-methylpiperidine, something as small as N-methylpiperidine, the methyl CH versus the methylene CH, the blue and the red CHs. So if you want to activate one of these selectively over the other, it's actually a huge challenge if you simply look at the bond dissociation energies. 91 kcals for the red, 92 for the blue. It would be difficult to get selectivity between these two positions purely on the basis of thermodynamics. Alternately, people have in the community, and the top two examples are from Abby's group, there's an example from our group, activated the methyl selectively in spite of this difference in bond strength, this tiny difference in bond strength. Photoredox catalyzed nickel cross coupling for N-methyl and ethyl aniline goes selectively for the methyl. Some of Abby's work, acylation does the same for the methyl. This is a nice example. The methylene on 2-methylpyrrolidine is selectively activated over the methine. So clearly all of these, including one from our group, this morpholine and piperidine derivatives, are methyl selective. Nate Dewey reported a nice example here, which has a methylene and a methine, and a photoredox catalyzed reaction goes selectively after the methyl. Every example in the literature is methyl selective. I would argue, as a community, we want complementarity. So we want a reaction that goes after the methylene. So how do you do that? So this is a problem in enolization chemistry that has been around for as long as we've been interested in treating ketones with strong bases. And in fact, the early solution to it is right around, I think, 50 years old now, where if you take something like alpha-methyl cyclohexanone and treat it with LDA and TMS chloride, it's exquisitely selective for the kinetic enolate. Of course, it's silicon trap, so it's enolsilane. If you do it under equilibrating conditions with a slight excess of the acid, triethylamine and TMS chloride, it's not very selective for the thermodynamic enolate, but you can fish it out. So what, 4-to-1 selectivity or so. This is Herb House in the late 60s. So why this thermodynamic works is because the enolate is long-lived enough that it protonates with the conjugate acid of the base used to deprotonate it, all right? And sometimes it's just excess ketone lying around. So we took an insight from that, and we thought, really what we want is to equilibrate these things. So Yang, a talented postdoc in the lab that arrived from Ruben Martin's group, took N-methylpiperidine under photoredox catalyzed conditions, iridium photocatalyzed blue light, acrylate as a trap. He gets about 2-to-1 regioselectivity favoring the N-methylpiperidine. Very good chemical yield, but poor, clearly, regioselectivity favoring the wrong one. And just to walk you through how this works, or how we think it works, the tertiary amine is oxidized to the radical cation. This greatly acidifies both of these positions to the point that a base comes along, guided presumably by sterics and a kinetic deprotonation. That generates this radical selectively over the secondary, over the methylene. Acrylate trap, of course, the reduced photoredox catalyst gives an electron back. It picks up the proton again, and that closes the catalytic cycle and gives you the product of the Giese conjugate addition. So what we need to solve this problem is figure out a way to equilibrate these two radicals and hope that something will drive the reaction from this secondary radical over the primary N-methyl radical. And Yang is a smart guy, and he found pretty quickly that this can actually be accomplished if you add triisopropyl silyl in co-catalytic amounts. So this inverts the selectivity from 2-to-1 favoring the methyl to 17-to-1 favoring the methylene, completely methylene selective. I'll talk about why this works in just a second. Let me show you how this works. So the top examples are all without the thiol catalyst. So just to give you kinetic selectivity, dimethylethylamine, 6-to-1 selectivity for the methyl. N-methylpiperidine under these optimized conditions, 1-to-1 roughly. Diisopropyl methylamine, 122-to-1 selectivity for the methyl, exquisitely selective for the methyl. Hunig's base, 5-to-1 for the ethyl. And ethylpiperidine, which has, of course, 2 nearly identical methylenes, is almost unselective, very modestly for the ethyl part of the. You add the photocatalyst, you add the silyl thiol to it, and it inverts in every case. 6-to-1 becomes 15-to-1 the other way. 1.3 becomes 30 to 1 the other way, 122 to 1 becomes 1 to 11, etc. Even this unselected one actually inverts slightly. Clearly the energy differences here are tiny, but there's something that drives it to the other position, which again, we'll talk about that in just a second. And in case you're curious, these aren't just photoredox catalyst conditions. So there's two complementary sets of reaction conditions. There's, of course, the traditional photoredox catalyst ones. There's also, at elevated temperatures, AIBN as an initiator in the presence of a silyl-thiol. This does not involve, we believe, no, it does not need oxidation of the nitrogen. This is probably by HAT chemistry through the silyl-thiol. You can trap things other than, of course, just acrylate, vinyl sulfones. This is dehydroalanine. This is alpha-trifluoromethylstyrene. Selectivity is parallel to what you'd expect. You don't go alpha to the ketone, you go alpha to the nitrogen in this case, etc. 5-membered rings, diaza heterocycles, and of course you can talk about other groups. Last structure here, under photoredox conditions, these are known to lose TMS plus. To give you a radical at this position, we generate the product where the TMS stays intact because of this HAT chemistry. How does the mechanism work? So we left the acrylate out of the reaction in the absence of thiol in presence of deuterium source. So this is just D2O. We get no deuterium incorporation. When we add D2O, and excuse me, when we add the TIPS thiol, the thiol exchanges with D2O, and that leads to deuteration at both positions. And that suggests that the CH activation is clearly reversible. In the presence of the acrylate trap, we get extensive deuteration in the products, in both products, and we get unreacted starting material that's deuterated at all positions, the 2 methyl positions, and in particular the internal methylene. And that suggests that the CH activation is completely reversible, and what's driving product selectivity is the trap onto the acrylates. And I started this whole talk with talking about how we need to go after modification of actual pharmaceuticals, so-called late-stage functionalization, and Yang has looked at these as well. So these are all precursor active pharmaceutical ingredients that we bought, treated under these reaction conditions, and the alkylation happens always internally. On much more complex settings, when there's a pre-existing stereocenter, we can't control it. This is an example that Nate Dewey used earlier when after the methylene, and we get alkylation at the, excuse me, after the methyl, we get alkylation at the methylene. Selectively tertiary positions, and again, much more complex systems, selective. I'll stop there. Of course, this is a Zoom talk, so I have to have a Zoom group picture that I think all of us have now. Really, I'll focus on the work of, I guess I'll thank the funding agencies first. It's NIH, as well as several industrial funding agencies. The work I talked about was exclusively the work of 2 people. That Hung Wei, whose half his head is here. He likes backgrounds that involve me in it, as well as Yang Yang. I'm sorry, I don't see Yang Yang, who did not make this picture. I thank them for their hard work and nice contributions. Lastly, thank you very much for the opportunity to talk to you from the comfort of my own home. And if there's some time, I'm happy to answer any questions.
Thanks very much, Tom. Great talk. Very nice indeed. And many of the questions start with that too. So there are several questions related to this general theme. So I'll read the one by Catherine Carter. Really nice work. Have you looked into developing asymmetric variants for your iridium catalyzed nitrine chemistry?
We are doing that right now, actually. I think, as you may know, we've been involved in metalloenzyme chemistry. This chemistry works in a metalloenzyme setting. It's not, I would say, ready for prime time yet. There are other, of course, technologies out there that you can also imagine for this, and I suspect would also work.
Okay, great. A question from Martin Colan, also saying very interesting talk, so that's a common theme. Were you able to separate the regioisomers of allylic amination quantitatively?
In the huge majority of cases, yes. These are all, we characterize them, all of them, to analytical pure. Do I remember a problem for any of them? No, not off the top of my head. It's certainly possible, of course.
Okay, and then a question from Hannah Slocum. Again, saying thanks for a great talk, Professor Rovis. Maybe it's sarcasm, Tom. I don't
think
know. Thanks for a great talk, Professor Rovis. Is there a reason that you believe the terminal alkene amination goes through an inner sphere mechanism over outer sphere?
Yes, so I didn't talk about that. I showed you the crystal structure of the sulfonamide trap, and we do generate, this is Toslazid chemistry, we do generate sulfonamides, of course, and we've done a competition experiment where we have a sulfonamide with a substituted sulfonyl that is in sulfonamide, benzene sulfonamide instead of toluene sulfonamide. And we get exclusive amination through the sulfonyl partner, and that suggests to us that it has to oxidize the iridium, and that suggests most relevantly that it's probably still on iridium when it gets delivered internally. We've also done an experiment where we've taken that sulfonyl crystal structure that I showed you and took a look at the KH over KD in a stoichiometric reaction for the amination, and then compared it to the KH over KD in a catalytic reaction for the amination. And they're the same, 2.7 versus 2.6. And that suggests that there's a unified mechanism for the two, that it probably goes to that intermediate that I drew.
Okay, question from Roundy Quivedo. In your late stage functionalization alpha to nitrogen, one of your examples shows selective functionalization alpha to the tertiary amine instead of alpha to an amide. Do you get very good selectivities for tertiary amines relative to doing alpha functionalization to amides, sulfonamides, etc.? And why?
Probably stability of the radical. These are weaker bonds at that position than alpha to the amide.
Okay. And then a final one, I hope you're getting the right affirmation that one is hard to get in a sort of virtual, because this one also starts off with great talk. In the amination of 1,1 disubstituted alkene chemistry. So you think the alkene substrate controls the regioselectivity. Is it possible that catalyst or ligand have some effect on the good regioselectivity?
Oh, of course. And I glossed over the catalyst scope slide. Absolutely. The weak catalysts on that slide, by the way, were 2 to 1, I think, or 1.6 to 1 regioselectivity. Absolutely, the catalyst has a lot to do with it. But I guess the way we look at it, and again, when you peel away the substituents on the CP, there's a huge electronic effect at the metal. And we're exposing the metal to be very sensitive to substrate electronics. And we found this, I had nothing to do with it. Hungwei found this nice solution where he's letting the catalyst discriminate between two groups that are really very similar to the point that he gets these high regioselectivities in the activation.
Okay, great. Well, Tom, thanks very much for a lovely talk, a great finale to this session. And indeed, thanks to all of the 3 speakers. We've had 3 really outstanding talks, different topics, but really come together extremely well. And at this stage, if now that we've got our prototype sorted out, we would have everyone clapping or whatever to really show appreciation for the 3 great talks we've had. So once again, thank you for the 3 speakers, and thank you for a wonderful audience. We were over 1,100 at one time, so that's a fantastic number to be joining this focus type of symposium. So great to have you all joining us, and hope everyone is keeping safe, and hopefully we'll see you again at the next symposium. Okay.